In this work, we present a novel recursive filter approach that allows higher modeling flexibility. Filters are still widely used in mobile robotics, and recent work in state estimation for robots such as legged robots or aerial robots still strongly relies on filter-based approaches. However, if we consider the type of information these platforms may use, we can observe a high variability in terms of sensor modalities, system dynamics, or prior information. Deriving statistical models which accurately capture this information and at the same time can be integrated in filter framework is very challenging. For traditional Kalman filters, one limitation is the requirement for an explicit prediction model. In other words, a model that predicts the distribution of the current state given the distribution of the state at the previous time. We can have a look at the following toy example in order to illustrate the problem. Let's assume that we have a robot in 2D which measures its forward velocity or speed, angular rate, as well as its x and y positions. If the estimated state is composed of the robot position and orientation, we can derive the prediction model on the left side. Illustrated by means of a Bayes network, this would look as follows. This could be used within a relatively simple extended Kalman filter in order to estimate position and orientation of the robot, even though the orientation is not directly measured. However, if for instance the rotation rate is not measured, the problem becomes much more difficult for regular Kalman filters. This is caused by the requirement for an explicit prediction model, meaning that we need to provide a prediction for the orientation despite the absence of rotation rate measurements. On the other hand, if we have multiple measurements of the rotation rate, this may also cause problems since a traditional Kalman filter cannot deal with multiple predictions. Here a simple approach would be to average the rotation rate measurements and adapt the noise parameter, but this may not always be possible. For instance, already having to deal with measurement biases will make the problem much more difficult. We propose to solve this problem by formulating a maximum likelihood problem over two consecutive states. This is equivalent to two-state sliding window batch estimation and can be illustrated by means of a factor graph. Now the available information, be it in form of sensor measurements, system dynamics, or priors, can be formulated as residuals depending on the two states. Based on these residuals, we derive recursive filter equations which effectively take care of inference and marginalization. The overall approach provides a high modeling flexibility which allows us to avoid the need for state augmentation, the use of invented state dynamics, or the suboptimal preprocessing of information. By showing the application to two different state estimation problems, we demonstrate the flexibility of the approach. If you want to get further details or see how we integrate dynamic cues on legged and aerial robots, please visit our poster stand.